Okay, hello. At the very end of class on Monday, I passed out a packet called the complex roots packet, except I forgot to pass it out in period 8. What is this packet all about? It's all about polynomials and finding roots of polynomials. And in class on Monday, in all classes, we did a big proof. Well, we did two things. We reviewed the properties of the basic properties of complex numbers, and then we proved this theorem that says that complex roots come in conjugate pairs. And just really fast, because that's a prerequisite for what we're about to do, what it says is that if you have a polynomial, I used a cubic, but there's nothing special about it being a cubic. This applies to any polynomial of any degree. If your coefficients are all real, so that part is important, if your coefficients are all real, but your roots are perhaps non-real, then the following pattern emerges, which is if you plug some number into this polynomial, like r plus si, for example, and you get back some really complicated output, like p plus qi. So in other words, plug this complex number into this polynomial with real coefficients and get back this complex number. Then what we showed is that if you plug the conjugate into that same polynomial, so this is kind of like an if-then situation. If you plug the conjugate into that same polynomial, then what you get back is the conjugate. Okay, so this took us like 15 minutes to establish this theorem by proving all kinds of properties of the conjugates, such as the sum of the conjugate of the sum is the sum of the conjugates, the product of the of conjugates is the conjugate of the product, etc. And anyway, the exciting part of this was that on the other hand, if I plug in some complex number and I get back 0, then I should say f. If f of r plus si is 0, then f of r minus si has to be the conjugate of 0, which is 0. In other words, as I said in most classes pretty clearly, if you plug a particular complex number into this polynomial and you get back 0, in other words, that's a root, then the conjugate of that will also be a root. This is summarized in the sort of catchphrase, complex roots come in conjugate pairs, as long as the coefficients of your polynomial are real. Okay, so this is a thing that you maybe even somehow were told already, but now in class that we proved it. What can I do with this information? Well, here we have a problem, and it says that we have a 5th degree polynomial. I forgot to write that. 5th degree polynomial. And then we're given a whole bunch of information. All the information that we're given is written here in black. Okay, well, we are told, and specifically, this polynomial has real coefficients. So since the polynomial has real coefficients, then the theorem that we were just discussing applies. And if 4 minus I is a root, I immediately conclude that 4 plus I is also a root, because complex roots come in conjugate pairs. 2 is a root, and I'm also being told that 5 plus 2i is a root, which means that 5 minus 2i must be a root also. Okay, so this polynomial has 5 roots now. 1, 2, 3, 4, 5. And so you might think that we are then completely done, because it's a 5th degree polynomial. A 5th degree polynomial has to have 5 roots, I guess. And what more is there to do? Well, okay, it's not quite true that just being given the roots of a polynomial means that you know the rule for that polynomial, the formula for that polynomial. Of course, what if I gave you a quadratic and I told you that the roots are, 2 and 5 or something like that? Well, do I now know every single thing there is to know about that polynomial? Well, no, because 1, 2, 3, 4, 5, you can sort of think about a picture of this. What do I know about this quadratic? I know that, that it goes through 2 and 5, but just knowing the roots of a polynomial doesn't mean I know that polynomial, because of course there are an infinite number of of polynomials which pass through 2 and 5. So for example, it could be like this one, but it also could be something a little bit more like this, cha-cha-cha, and it also could have leading coefficient negative, in which case it would be upside down, etc. So all of these little things are possible, and therefore, what do I know when I know that 2 is a root and 5 is a root? Well, if we apply the factor theorem, what does the factor theorem tell us? The factor theorem tells us that if 2 is a root, then x minus 2 is a factor. And since 5 is a root, x minus 5 is a factor. And so we actually have some justification for this move that I'm about to pull, which is kind of common sense, which is to say that if I have some quadratic polynomial that goes through 2 and 5, then it must be the case that that function is of the form x minus 2, x minus 5. But what I don't know is like this leading coefficient. And so if there are an infinite number of quadratic polynomials that have roots 2 and 5, if a is like 1, perhaps it looks like this purple thing. If a is like a third, perhaps it looks like the red one. If a is negative 1, perhaps it looks like the green one, etc. And okay, I know that it must look like this because the factor theorem tells me that one factor of this polynomial is x minus 2, another factor of this polynomial is x minus 5. Okay, so hopefully that's pretty clear. Therefore, for this problem, I'll just erase this now. For this problem, since I'm given 5 of the roots, and it only has 5 roots, then the only thing really that we have to do is find out what that a is. And this is how this f of 1 equals 400 comes into play. Okay, without further ado, let's do it. Let's see how much space I'm going to have here. Sure, that's plenty of space. So let's go. I'm going to write out this polynomial. What does it look like? Well, the one thing I don't know is what a is. Other than that, I can now apply the factor theorem 5 times. So since 4 minus I is a root, it must mean that x minus 4 minus I is a factor. That's the factor theorem. If 4 plus I is a root, then x minus 4 plus I is a factor. If 2 is a root, then that means that x minus 2 is a factor. If 5 plus 2i is a root, then x minus 5 plus 2i is a factor. And finally, if 5 minus 2i is a root, then x minus 5 minus 2i is a factor. Okay, so this has been written out kind of in this big disgusting format. How can I simplify this a little bit? You could. It wouldn't be wrong, it would just be a bad idea to plug x equals 1 in right now and set it equal to 400 and solve for a. But instead there's like this technique, and the technique goes like this. I'm going to distribute this negative through. And instead of this being x minus 4 minus I, this is really like x minus 4 plus I. And here we have x minus 4, this becomes x minus 4 minus I. Okay, and then by regrouping slightly, chomp and chomp, what I have here is a product which has the difference of squares format. Another way of putting it is these two are conjugates of each other. X minus 4 plus I and x minus 4 minus I. And so it becomes very nice and simple to multiply these out. And so, okay, when we do that, what do we get? Well, we get x minus 4 times x minus 4. So that's x minus 4 quantity squared. And then minus I times x minus 4 plus I times x minus 4. Of course, this is the difference of squares. And then minus I squared. Okay, and now maybe we just do this again, or let's just keep going. Why is this a good idea? This is a good idea because now all the imaginary numbers disappear. And what do we have here? If you want to expand this out, you can. You don't have to, but this becomes x squared minus 8x plus 16, but then I squared is negative 1, so minus I squared is plus another 1. So this becomes plus 17. And This is still x minus 2, just kind of like rewriting this like this. Okay, now we just do this whole trick again, right? What's the simplest way to multiply this by this? Well, again, you just move the parentheses, so to speak. So that becomes x minus 5 minus 2i, and then you think of those as being one thing. And then this is x minus 5 plus 2i. In other words, and this is always going to happen because these two numbers are always conjugates of each other. When you distribute the negative and regroup, these are conjugates of each other, or they're in the difference of squares format. Okay, so now I can multiply through here, and when I multiply through, x minus 5 times x minus 5, x minus 5 squared, I'm going kind of slow here, x minus 5 times plus 2i, so that's plus 2i x minus 5, minus 2i x minus 5, so those two will cancel, and then I get minus 2i times plus 2i is minus 4i squared. Okay, and then this can be expanded as x squared minus 10x plus 25, but then I squared is negative 1. So that's minus 4 times negative 1, so that's plus 4. So this whole thing becomes plus 29. Okay, what have I accomplished? Basically, all I accomplished was writing out this polynomial in a form in which no imaginary numbers appear anymore. Okay, so this really only takes like 2 or 3 minutes, and I think is totally worth it. Now, finally, I return to this extra little piece of information that I have, which is that f of 1 is 400. Okay, there are slightly different ways to do it, but this seems good to me. So if I plug in 1 here, I get a times, what is all this? Well, that's like 1 and 17 is 18, minus 8 is 10. Here, if I plug in 1, I get negative 1. And here, if I plug in 1, I get 1, and 29 is 30, minus 10 is 20. And all of that, when I plug in 1, is supposed to be 400. So I have this equation to solve now. This equation says negative 200a is 400. And from this, I conclude that a is negative 2. Okay, so the entire point of this problem was to write out the rule for this polynomial, and the answer is this 5th degree polynomial has leading coefficient negative 2, and then personally, if I were you, I would just leave it like this. There are many different ways to write this, but this is one way to write it, just like that. So that is precisely the 5th degree polynomial, which has these 5 numbers as roots, and which also satisfies f of 1 equals 400. Okay, hopefully that made sense. Goodbye.